Okay, so now we will try to understand the steady conduction in plane walls, and we'll try to develop the thermal resistance network for different types of setup. So here we have the wall. You can see this is solid. The temperature is T1, it is T2. This is the atmospheric air. This is the atmospheric air in this section. So we can say this is the atmospheric air. The temperature is T infinity 1, T infinity 2. We can simply say it is the high temperature zone, because if you see it is how the temperature gradient, you see the temperature profile here, how it is changing. So this is the top point, this is the bottom point. We can say this side, the left side, it's the hot fluid, it is the cold fluid. We can see some linear temperature gradient here. So what is happening in this case? You look, this is air, this is, you know, the wall, the left wall, left side of the wall. So we can say the heat transfer in this section, it is actually due to the convection. We know the definition of the convection and conductions. Here what is happening, you see this point and this point, it is solid, so it will be conduction, and again in this side it will be convections. So it is convection, it is convection, it is conduction, because this is solid and here it is fluid. And so we know this definition. Now if you want to develop a network and if you want to analyze the overall the rate of the total rate of heat transfer, then we need to analyze, we need to calculate the total thermal resistance. So we'll develop a thermal circuit at first. So let's say this is T infinity 1. So this is T infinity 1. This is T1, T1. So in between these two, we have a thermal circuit. And here, what is happening? The convection is the heat transfer medium. Now, for this point and for this point, T1 to T2, we have another thermal circuit. It is the convection. So we said it is resistant of the wall. So this is wall resistance, or this is resistance due to conductions. For this T2 to this T infinity 2, it is the convection happening here, so it is convection. So the total rate of heat transfer formula, we know it is equal the temperature difference over the total thermal resistance. So we need this total thermal resistance, and we know it is actually this, this, and this. So basically it is the sum of this one, this one, and this one, because it is the overall the thermal profile. And now we already know the thermal resistance coefficient for convection, or thermal resistance due to the convection, it is 1 over H A, and for conduction it is L over Ka. You can remember it from the previous video. This is for convection, this is for conduction, so we just substitute the value here. You see 1 over H A, L over Ka, 1 over H2A. So this is, we said the temperature T infinity 1, we said H1. It is 2, we said H2. You can define it whatever you want. So this resistance total, put it here, and then you will get the total rate of heat transfer. Now if we have two layers, so this is the wall 1 and wall 2, definitely this is conduction, and this one, it will be convection, it will be convection. If you can just recall your understanding from previous, it is the air, so convection. This is solid conduction. Here we have the air, convections. So the total, it will be, you see, this convection, this wall 1 resistance, wall 2 resistance, and this is convections. You see, we put this is convection, and the middle two, it is conduction. Once you have this total, just put it here, and then you will get the total rate of heat transfer. Now it will depends when we have multiple layer of walls. So then for multiple layers, if we have the smooth connections, that's fine, but sometimes you will have some imperfect connections like this. If we zoom in, you see it will be like this. So then we need to actually consider there will be some thermal resistance here, so we need to consider that one. So for these types of thing, here is the formula. The thermal resistance for this imperfect connections between two walls, it is the temperature difference between this point, that means this side and the other side, over the heat flask. So what you need to do when you will develop a thermal circuit, you need to consider this section. So this is solid, it is convection. This is sorry, conduction. This is solid conduction. Here we have this. So if I just draw a thermal circuit for this, so it will be the total resistance. It will be the resistance for, let's say this is wall 1, then this contact resistance, that means this one, and the resistance for wall 2. If I say this is wall 1, this is wall 2, so it will be the network. We'll solve problem during the lecture and tutorials. If you have cylinder or spheres, for cylinders, you see this is the center, outer radius, inner radius, so temperature, inner temperature, outer temperature. So the resistance due to this thickness, from theories, it is the resistance, the thermal resistance. What you need to know? You need to know this formula for cylinder. And once you know this, you can put it here. You will get the total rate of heat transfer. For spheres, here is the formula for thermal resistance. So once you know this, then you just put it here, and then you will get the value. Now, if you need to develop a thermal circuit, so let's say it is the center. Here we have fluid, so it will be convection here, it will be convection here, and the conduction here. So the total resistance, you see the formula: convection, convection, and this is the conductions. So if once you know this for cylinder or sphere, you just put the corresponding thermal resistance value like this. Okay, if it is cylinder, put that, sphere, put that, and now this is the total formula for the heat transfer. It is T infinity 1, T infinity 2 over the total resistance. So we will get the total resistance from here. For cylinder, it will be the formula. For sphere, it will be the formula. If we have a multi-layers cylinders or spheres like this, let's say this is layer 1, layer 2, layer 3, then how we'll calculate? So in this is the center. Okay, so here the temperature is T infinity 1, here T infinity 2. So in this section, what it will be convections. Here it will be convections, but here conduction. This is conduction, this is conductions. So we will have 1, 2, 3, 4, 5, total 5 layers. You see here convection, convection, and the middle 3 is conductions. We can calculate the total resistance from here. When you will put it here, you will get the total resistance. Just substitute it here, then you will get the total rate of heat transfer. So that's all the theories I quickly tried to explain. I believe this is super easy. When we'll solve more problems during the tutorial and lecture, it will be clear to you. So go through the books, you'll see a lot of problem over there, and just practice this problem. So that's it for now, and we'll discuss it during the lecture and tutorials.